So last time we finished up chapter 7. So are there any questions over what we did?
We did? Oh my god.
Last time, yeah. The pace.
We don't need to know this anymore then, right?
What's that?
We're done.
We don't need to know this.
In there, yeah, exactly.
Ever?
Wipe it from your head.
Okay.
Thank goodness.
Unless you want to pass further tests.
Oh, plan?
In which case you might want to hold on to it.
Well, I think I'll reconsider that.
While I'm still
I might need more room on my hard drive. And new stuff. Oh my gosh. Okay. This is new. I think I need more paper.
Stan?
Yeah, when you were. I only have one piece of paper left. Let's go online and buy some notebooks.
Scrappy people and punk ass.
So, yes, we still need to know these. In fact, the next test is going to involve, like the double angle formulas, the half angle formulas, all the other stuff we did in chapter 7. Everything above that black line, except for the tangent stuff, you can pull down. We talked about that last time. I don't make you memorize the tangent stuff because, again, I don't have them memorized. If you want to, feel free. But you can always get them from what you know about sine and cosine. If I ask you questions, obviously, about the product to sum or sum to product, I'll give you those, right? Because that's what I would want to do for myself if I was in this class. So I'll do this. I will do that for you. Everything you have to memorize, obviously, you got to memorize. Are there any questions over chapter 7? It was easy.
Oh no.
Easy. So easy. So let's do a couple more problems out of that last one, I think.
Okay.
I'll pretend like I had some questions from there.
That sounds like a good idea.
Because I would expect questions from there.
Can you do chapter, like, page 514, number 12? Cosine to the fourth x.
Yeah, so that's your, they call it the power reducing formula, lowering powers.
Let's see if I did that right.
So the thing that'll make you memorize is the, like sine x. Sine, let's write this one. What's the half angle formula? Who knows that for sine?
It's for sine?
1 minus cosine 2x over 2.
Good. And that actually comes from, so one thing you guys got to get really comfortable with is this sets up a general rule. Whatever is here, twice that goes there. That's the general rule. So if I have x there, this would actually look like 2x, exactly. Whatever's there, twice that. So whatever's there, twice that goes here. This happens in a lot of mathematics where we set up a general rule, but people get so hung up on the specific things that are in there. No, it's the general rule to really pay attention to.
There is no radical in the book. There is no radical for this idea.
I know. Don't worry. There is. The one I'm talking about, there is. This is the half angle formula.
Sine x squared.
We're trying to make it look a little bit more like the one we have to use. And I didn't make you guys, if I square both sides, then you end up with
Sine squared x.
that thing. Right? For example. The one we're looking at is the cosine equivalent. And that, of course, looks almost the same, except here there's going to be a plus. So on this problem, it was cosine to the fourth, right? So if I have cosine to the fourth, and I know that cosine squared x is this, you just have to use it a couple times. Cosine to the fourth x is cosine squared times cosine squared. So they can rewrite each cosine squared as this and just multiply that out.
Oh.
So if you had cosine to the 6, you'd have cosine squared. You have 3 of these things, and you have to multiply that line out. Don't let that be a huge deal. It really isn't.
I'm not sure if you did it right.
So it's the same thing as if I had sine 4x. Well, I know sine 2x is what? We talked about this the other day.
1 minus cosine.
2 sine x, cosine x. So the rule is whatever's here, half of it goes here and here. And that 2 we know is there because it comes from the 2 parts of the sum formula. Right? So the rule here is not that 2 goes there. The rule here is half of this goes here and here. So how would you do sine 4x? So it would be 2
sine 2x.
2 sine 2x, cosine 2x. And then if you had to go further, you can use that rule one more time here. And then you got really 3 kind of rules you can choose from for cosine 2x. Do you remember that? Cosine 2x, there's 3 different things that could be. And those are 3 that you have to memorize. I memorized 1, cosine squared minus sine squared, and then build the other 2 on top of that. And you do hit places, let me see if I can find the problem real quick. So here's what I'm talking about. Cosine 2x is cosine squared x minus sine squared x. That's all I memorize. Cosine squared is also how related to sine squared? Yeah, 1 minus sine squared. So 1 minus sine is 1 minus twice sine squared. So the cosine squared must be the other way around. I'm sure if I tried to, I can memorize those. But I just haven't done that yet. Let's memorize that thing and then build those when I need them. So if I have a problem where I've got cosine, I've got to solve this equation. Let's not do that. If I had to solve this equation, 2 things are kind of showing you which way to go. One side has a double angle, the other one doesn't. And you want those to kind of match up to make this a little easier to work with. So that's what's telling you to rewrite this. Also, which one do you pick? Well, this has got sine squared. So you pick the one that's got only sine squared in it. So you don't bring in any other stuff. You may have like terms. That's the kind of stuff that's driving you what to do. So I can replace cosine 2x with 1 minus 2 sine squared x. And then I can go from there. Does that make some sense? That's why it's kind of nice that we have 3 options here. That's what I'm trying to say. I would not want to use that option here because then it brings in a cosine squared I really don't want to mess with. Now I can add my 2 sine squared x over there. I got like terms. Sweet. So let's do this. Let's look at solving some of these freakier looking equations. On page 528, probably 529.
Did you answer number 12? Or you have to do it all times it all out?
Which one?
The
Oh,
one
yeah.
that-
You've got to multiply it all
Oh,
out.
yeah.
Yeah, that's all. So the short answer is no, I didn't answer it. But I showed you how to get it. So if I had this equation to solve here, so I've got to solve this equation. This is section 7.5. 7.4 and 7.5 are basically the same thing. They're solving equations with trig functions in them. 7.5 says, oh yeah, you might not always have x or theta. You might have 3x or 4 theta. All right, so it's just expanded on the same idea. But sometimes I don't want to deal with 2 theta. We normally kind of keep that till the end, and when I get 2 theta, just divide by 2. Right, so what we saw last time? Well, what's something better I could do? I can't even solve this really, because I've got kind of 2 opposing viewpoints as to what my inputs should be. I got theta in one and 2 theta in the other one, so what should I do here?
Change 2 theta.
I'll take it one.
Yeah, break this down so it's just in terms of theta. So sine 2 theta I can write as 2 sine theta cosine theta. can you do there? Yeah, factor. So all the same rules of solving equations still could come into play. And we saw that when we saw equations with logarithms in them and exponentials in them. We sometimes had to factor these things, right? Either the 2x plus either the x, you could factor that. So how do you factor this? Take a cosine out. You get either cosine theta is 0 or
2 sine theta plus 1.
2 sine theta plus 1 is 0. Right? I mean, that should feel very familiar. Hopefully, because it is. In fact, you could look at this. We did trig here, and that's the only real trig we've done in this problem yet, because then the rest of it was basically just factor, zero property rule, or whatever the hell your book called it when you took algebra. And now it's still algebra. Well, this one is still a little algebra. On this one now we can apply some trig. When does this happen? Cosine theta equals 0. Pi over 2 and 3 pi over 2. The really nice thing about those, though, maybe I don't need this. Pi over 2, 3 pi over 2. So I'm going to write the general rule then. I don't really need this one, do I?
So pi over 2 plus pi k.
Because to really get this, I can always take on both of these, I can say plus 2 pi k always. And that will bring me back to my self. But I stop halfway or a quarter of the way if it makes sense. If I can stop and pick some other people up and then come back to myself, I'm going to do that. Here I can. And we saw some situations where we couldn't. There's just no way to stop, and then I don't want to stop again and pick. Nobody's there. I don't want to pick people up there and there. It freak me out. So I can't. This one I have to do 2 answers for, but this one I don't need to. I can pick up all of him at the same time. So it'd be pi over 2 plus
pi k.
Pi k, because I have half rotation, or in reverse. And we're not quite done.
Why'd you say that it's not 3 pi over 2?
It is. But I don't need a separate line for that answer because I can pick those answers up here. So I'm glad you said that. I'm not saying that's not an answer. I'm just saying we actually get that answer in one step. So what about the other piece? We're not done yet? Oh, sorry.
Okay. Would you be wrong if you put both answers? Or?
No. I said that before. It would technically not be wrong. But if you did it more than once, I'd have to say something. Because it's sort of convention to have your answer in simplest form. And so if you have 2 and you really don't need it, that's not simplest form. So that is one thing just to consider. And of course over here, what's true here? What quadrants am I in for this to work?
3 and 4.
Yeah, the lower ones, 3 and 4, for the y piece to be negative. And the reference angle has to be what?
Pi over 6.
5 or 6. It's got to be closer to x because that's where sine is smaller because it likes y, doesn't like x, right? So this would be pi over 6 reference angle. So what are my 2 angles I'm talking about then?
7 pi over 6.
Yeah, just pi over 6 past the whole pi. 7 pi over 6. Pi over 6, almost to 2 pi. 11 pi over 6. And this is a good situation where I can't pick this other dude up and then have the same step to get back to myself. I can't do that. So I do need 2 separate
Plus 2 pi.
answers
4.
here. Does that make any sense? I think
Yes.
some of you understand and some of you are humoring me, and that's great. But I think back to when I learned this, and I'm like, my teacher never said that. And that's what I try to do when I teach this, is the things I wish my teacher would have just freaking said, I try to say them. So here you just say, on both of these, you have to do the complete rotation, so they're both going to be 2 pi k. So the whole answer to this problem then is that. Now, every now and again, you actually might be able to capture, like this in here or something that obviously did not happen here. And if you don't see that, I'm not going to ding you on that. But that is one more way to consolidate things possibly. Yeah.
Something that's more than 1.
If you're talking about cosine and sine, yeah. But cosecant, secant, tangent, cotangent, they could all be bigger than 1. But if you had, I know what you're talking about. You're talking about something like, oh, let's see. You can do it, Jeff. Can you? Maybe. And actually, I've seen, yeah, you could actually do something a little less, a little more specific. I was going to say less non-specific. That's too hard. You can do what's called, whatever you want to call that. Replace sine with S, cosine with C, or you can replace the whole damn thing with U. Whatever makes more sense. And the only reason I would do that, I probably wouldn't do that because my S's and my 5's are essentially the same symbol. So it might not, it looks more like a snake or something. I don't know what that one. Really good old movie. Title was. So how do you factor this?
-5 -1.
S
Minus what?
-6
minus
plus
6
1.
plus 1.
Yeah, S minus 6, S plus 1. So sine theta minus 6, sine theta plus 1. So here you get sine theta equals 6, and here you get sine theta equals
Minus 1.
this.
It's not a valid answer.
It's no good. It's the same thing as getting e to the x equals -1. That's not going to lead you to any answers because that's impossible, right? So that's not here though. So that's no good. It leads me to no answers. So that doesn't add anything to my solution set. This one will. When is theta? What thetas make sine theta equal -1?
3 pi over 2.
Yeah, just 3 pi over 2. That's the one place where sine is -1. So to capture all the answers, I just have to.
Plus 2.
There's no other people to pick up, so I've got to do a full rotation. How are we doing so far? Is that decent? I'm trying to remember if I can find one like one I was talking with somebody about earlier. Here, perfect. Ooh, yeah, that's ugly.
Well,
That's not too bad. 29. So there's a semi-general rule you can apply here. If you have any squares on a trig, that's directly related to an identity. I probably want to go in that direction. If you don't, you either want to break it down to sines and cosines, or you actually might want to end up squaring to make squares show up. So I'll do one like the second part I just said, because this is not one where I want to do that necessarily. So on this one, I have secants, tangents, cosines running around. I really need to kind of get them all to be the same thing. So they're like x. So I could do a u sub eventually if I wanted to. So how could I kind of work towards that?
U square equals 2 sec. U square equals 2 sec theta.
Yeah, secant is 1 over cosine.
minus cosine.
Tangent sine over cosine. So that at least looks a little better. Let's see if this actually gets us anywhere. And this actually, huh? It does, all right. So if you put these together, and at the same time how do I get rid of these cosines? You multiply. Is that cool? I did a couple things at once there. Don't like fractions, so I kill it by multiplying by cosine. Up it goes. And then how do I save myself here? Thankfully, like I just said, there's a trig function with a square on it. This is an equation. Oh, snap. You with me? This is not proving identities. And I'm with you, Charles. I understand. This is given to me as equals. And I'm trying to solve for what theta must be to make it to make that happen. This has to be equal. So I am able to add things and subtract and divide, all that kind of stuff with both sides. Proving identities, that's where you can't. You can't assume it's equal if you're trying to prove it's equal. Here, it's given to me that it's equal, and I'm just trying to figure out what the hell theta is to make that true. Is that how we doing so far? Is that cool? So you can totally do things to both sides here. Thank the gods. What can I do with something in here to make it better?
Or 1 minus.
Yeah, I've got sine, I've got cosine squared. I want everything either cosine or sine.
Or you should
The squared trig functions are related to identities, and cosine squared is also 1 minus sine squared. Do they always have the heat on in this room? Or is that just me? It's always the heat is on in this room. I don't know if you guys realize that there's a really, well, this will be nice anyway you look at it. You can, the ones will go away, you can add the sine squared over. Is that cool? See, now it's more algebra here for a little bit. You can factor that.
Take the sign out.
Alright, take the sign out. So then sine theta equals 0 or sine theta equals, bless you, 1. Cool. So this happens only in application of some identities, algebra, and then trig ideas. What actually makes sine become 0 if theta is 0 or pi? And that looks like something I can pick up. So 0 plus, so you don't even need a 0 then, but let me just keep it there for right now. 0 plus pi k. So you just make that pi k. And when does sine theta equal 1? Pi over 2, and that's the only place, right? So then you have to go a full rotation around to catch him again. 2 pi. 2 pi. Cool. Very separate. You can't intermingle those. There's no way to catch the other dudes with the one guy. So 2 answers. 2 families of answers. Let me say it like that. Cool. Is that? So of course, if you're uncomfortable with some of the algebra involved, that's bad for several reasons, but it's also going to make these very difficult. Yeah?
Can you explain why it's 2 pi again?
For that specific one, there's only one possible way to make this true. Inside of 0 to 2 pi, right? My base angle to make it work, and that's pi over 2. So how do I catch that same thing again? I have to go all the way around to catch it again. Or all the way backwards. So I got to go full rotation any number of times forward or backward. That's what the K does. Yeah. Whereas with this one, it was 2 locations. So instead of going around 2 pi there and around 2 pi there, I just went around half a pi, half a pi, half a pi. Not half a pi, but half a 2 pi. Half a rotation. All right. Yes, sir.
It's probably, is it 0 plus pi k because theta has to be 0 in order for sine theta equals 0?
Yeah, theta has to be 0 or pi.
Right.
Exactly. So I start with 0 and I can capture all the pi's. Yeah, cool. Okay. All right. So the other one, see if I can find it in here real quick. No, I'm not going to be able to. Liz, what was that one we were looking at that we had to square?
Yeah.
It's in here somewhere. I just don't see it. Oh, here it is. I got it. Okay, sorry. All right. So this one's really kind of funky. Because what's the actual identity involving tangent and secant?
They're weird.
Yeah, tangent squared plus 1 is secant squared. So this is not an identity because it doesn't have the squares on it. So we're trying to figure out are there any angles where you take the squares off and this is still true. So there's possibly specific angles where this is true. In general, this is not true for any angle, but maybe there's some angles where this is true. You try to start to attack this thing, and you could make this sine over cosine and 1 over cosine, but you find out pretty quickly that doesn't get you anywhere too good, right? Last time we did that, we had cosine squared, and we can rewrite that, and it was awesome. If you do this, you have sine over cosine. 1 over cosine. If you multiply by cosine, you get sine theta plus cosine theta equals 1. And that's almost in the same place that it was.
Squaring on both sides?
Yeah, exactly. So this is a square away from being identities going on. So if I square both sides, and don't get overly excited and square each piece. A plus b squared is not a squared plus b squared. So you got to FOIL this bad boy out. But the really nice thing is, what is secant squared in terms of tangent?
1 plus tangent.
Yeah, 1 plus tangent. Jeff, you need a plus tangent. There you go. And on this side, if I FOIL this out, I get tangent squared plus a couple of tangents in the middle term plus 1. I'm going to FOIL that thing out. Now this is doable, because stuff cancels. The problem is, do you guys remember when you had, if I put that up there, you should not have to do any work. But if we blindly went forward and we squared both sides and it's like, I got an answer. What's wrong?
Plus or minus.
No, I didn't take any square roots.
What's wrong?
Does that work when you plug it into the original equation? No. When you square both sides of an equation, you lose information about the negatives.
Right.
So math says, I forgot if that was negative. So 16, yay. If that was not negative, this would be good. But it was, oh shit. So I don't know if you remember, when you do radical equations, you must check your answers for extraneous solutions. Right? Not sure why I said all that. That word just is freaky. So here, the same thing's going to happen. I squared both sides of my equation. I lost information about where these things are negative. It makes it easy to work. Bam. So tangent theta is 0. So I'll show you what I mean here in a minute. Where is tangent theta equal to 0? What's on the top of tangent? Sine. So tangent 0 where sine is 0. And sine is 0 at? Sine is 0 at 0. We just did it a second ago at pi. And at pi, do both of these work, before you even start building off of these guys, do they both work in the original equation? Tangent 0 plus 1, we plug a 0 in. Tangent of 0 is 0, plus 1 is 1. Secant of 0 is 1 over 1, which is 1. Check. Okay, so that's good. When I plug a pi in, tangent of pi is 0, plus 1 is 1. What's secant of pi? 1 over cosine pi, which is negative. Oh, shit. Throw that out. So it's kind of, again, it's this whole idea of the process doesn't care what's in there. When you square both sides of an equation, you better check your answers. I don't care what the hell was in your equation in the first place. When you square both sides of an equation, you're hiding from math what the sign was. Do you see how we see that this is 1 equals negative 1? Math doesn't know that was a negative because we squared things on the way. So we can't hold it against math. We're coming up with pi as an answer. Like, oh, our bad. We had to square just to make it doable. Sorry, math, and we throw this thing out. And now to capture all the answers.
Plus or minus 2. Or plus 2.
Okay. Yeah, now this is where people get a little confused sometimes because you get too focused on what the trig function itself was. But if I'm at 0 degrees and that's my only answer,
2 pi.
I still have to go 2 pi k around. Right? Don't focus too much on the fact that tangent has a period of pi. That sort of comes in, but not always. It actually only matters where you are and the angle and how far you got to go to capture the next answer. That's what rules what the hell this is. Yeah.
What do you mean when you said that the period only kind of comes into play?
Because actually, if only we didn't have to square, tangent will always give you, well, pretty much always, give you answers that are 180 degrees apart. Right, so for example, if I had a much nicer equation like this, so if I had tangent theta equals 1, where's that true? Pi over 4? First quadrant, and also where our sine and cosine are the same sign again. Third quadrant, so pi over 4 past pi. So the other way around. So 5 pi over 4. See how they are? How far apart are those two angles? 180 degrees. And there's your pi. There's your period of pi. You with me? But this one has a strange place where I had squared just to get here, and that's why I had to throw one of them out. So I'm not always guaranteed that. So don't base this on the period of the trig function you're looking at. Base this on the reality of how far do I have to go to get to the next answer. Period. So to do this one, you don't need that one, right? Now I can do my plus pi k. So very, 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 very often tangent equations will end up with plus pi k because of their period. I agree with you. But don't look at it like, don't just automatically do that. Do that and say, okay, it is half a rotation. I can do that. If you have any sine equation, right? Sine, we did this one earlier. Theta is pi over 6, or where else? We did one. Oh, we did one on the other side.
Oh, it's positive.
5 pi over 6.
Yeah. So see that I have to do how much? Plus or plus? I almost did the same thing.
2 pi k.
2 pi k, right? And again, why is that? Because of the period of sine being 2 pi. But again, it all just depends on, is there another one half a rotation away or something? That's what really rules the day on the what you put here. You can't make it a general rule that sine and cosine will always be 2 pi, tangent cotangent will always be pi. You can't do that. Some of you guys are like, I wasn't even thinking about that, Jeff. I would just continue to not do that. I thank you. That's cool. Just keeping that up there, but it's cool.
It's all red, white, and blue. I don't know
All right.
what that is exactly. It looks like.
Is there anything else? Any other specific questions? Whew. Anything else? Any other questions from before we get into chapter 8? Yeah.
57?
In 7.5?
7.5. 520.
Oh,
Do we have
this one says use a graphing device, right?
graphing device. I have one of those.
7.5?
Yeah.
Use a graphing device.
57.
So guys, anytime it says use a graphing device to solve this equation,
Put it in your calculator.
well, yes, that's what that means. But you just, it almost doesn't matter what the functions are because the calculator doesn't care. It's just going to plug and chug and make tables values and connect the points. But you got to look for where those two, of course. You could and do the root. But again, I like to do this because then I can just put it on and go enter, enter. Instead of left cloud or right cloud. I might be overstating the actual work.
Oh, I think I'm in the wrong one.
So what Charles is saying is you actually could do sine 2x minus x equals 0, graph that,
There we go.
and look for the roots. That's fine.
Oh, how pretty that is.
Just personally, I like to look for the intersections instead. Who cares? Either way. Is that cool?
Put in radians there, Billy.
So on the test, last test, I had like inverse tangent of 1 over radical x and that, some ugly ass thing. So this should be relatively nice. Okay.
Two solutions, right?
And does that give you an interval?
But thankfully, x goes above 1 quickly.
Like,
So there's no way it can still intersect after
like 5 that way.
1.
You just have to find the intersect point x
Well,
of x and y. Both
there's
intersect points, like
couple
for
of them.
x itself and then y itself. That should be 3 of them.
No.
There's two.
To answer this equation, what variable is involved?
What variable?
Yeah, what variable is involved? The answers to this equation will be what equals something?
There's
X.
0, 0.
Right? So you don't give me the y's at all.
So only x.
Give me the x answers to this equation. Yes.
So 0 and... Look, there's 2 answers, right?
1, 2,
Three.
3.
Yeah. Or no?
No, 2.
I see
2,
2.
yeah.
0 and 0.947.
See that's tricky.
And of course, anytime you go to graph, make sure you are in radians. If you hit that graph button and nothing happens for a little while, you are probably in degrees.
If you subtract the x
Oh, there's
over,
three.
it gives you 0, 0 as an answer as well, which could trick
It is.
you.
But
It hits it there.
it hits 0, 0. It says it hits 0, 0.
And it does hit 0, 0.
Yeah.
So, okay.
So
There's
there's
fine.
3
3
answers.
answers.
Okay,
Yeah.
good.
Okay.
Okay.
Alrighty then.
All right.
So there's
See it up here for question. 1, 2, 3.
So now we're going to get into chapter
Muy bien, Billy.
8. And to be completely honest, we've already done some of chapter 8, believe it or not.
Oh, thank God.
Yeah.
There is apparently word problems in this chapter.
So, we don't get into 3 dimensions in this class, but, I mean, anytime we do something like this, the whole purpose of having this grid set up here is to identify this point easily, so I can say this point is 3, 3 relative to the grid I've set up. I could also have a point here, straight out, maybe like 10 up here, 10 off the board. So then I say this point would be 3, 3, 10. I just have to add one more. So how do you identify this point? 3. And then if I add another axis in there, 3, 3. And then if I go 3 off of that, how do I identify that point?
3, 3.
3, 3, 3. Right? So, I mean, that's the most we can do physically. You can talk about more dimensions than that, and math doesn't care. Math is 3, 3, 3, 3, 3, 3, or whatever. You guys semi with me still? So, I mean, there's a whole issue of, even when we do the graphs we currently do, we're not being entirely honest with how much it can do, because we can go at least one more dimension to still make physical sense. Right? Thank God. That'd be very strange to be living in flatland. That's not where we're going to focus on. We're going to focus on, is there an alternate way besides x, y to identify where a point is? So I got the point 1, 1, for example. Very exciting point. Is there some other way? And of course, we understand what that means. When I say 1, 1, we know that means go 1 on the x, and then 1 on the y, and then I get there. Right? I mean, that's nothing major. But why is it? That's definitely not the only way. And dear God, there's so many freaking coordinate systems out there, it's insane. And you pick the one that's best for the problem you're doing. So this is really crucial. We're getting to the point where the problems ahead of us might get really difficult in the XY coordinate system. So we might want to go to another coordinate system and do it in a different way. Right, so right now, you probably have no idea what the hell I'm talking about. But here's the idea. How else could I tell somebody to get there? I could tell them go 1 over that way, and then 90 degrees up from there, go 1 up from there. That's basically what 1, 1 says. But I could also tell them, I always start looking at 0. Turn, how far do you think I have to turn? What angle would that represent?
45.
45, right? Because I want to face this way.
It's also pi over 2.
I say, okay, okay. So turn at an angle of pi over 4, right? And then I have to tell them how far to go out. So I can use instead of xy, I can use r theta. Theta is how you turn. Where do I turn to? And then r is how far do I go out. Now be careful. How far would I go out? I like your thinking, but no.
1?
Square root of 2. Pythagorean theorem.
Oh, yeah. Okay.
I like that. Really. So in rectangular coordinate system, this point is 1, 1. In polar coordinates, this point is root 2 pi over 4. Now, understandably, that looks much more complicated than that.
Of course.
But the minute we accept and we understand that there are more than one way, there is more than one way to identify where a point is sitting, then we start to realize that has implications in other things. What else have we done on the coordinate? We graphed graphs. And they have corresponding equations that relate to y and x. So maybe now there are graphs of equations that are much simpler in polar coordinates. In fact, any graph that is any kind of periodicity or circular in nature, like a circle. A circle would be stupid easy in polar coordinates because that's exactly what polar is all about. It's about circles. How are we doing so far? Is that?
Yeah.
So we have the XY way of doing things, which is go so much out left or right, and so much up and down. Or we have the polar way of doing things, which is start looking at 0, turn and go out so much. I could tell the dude to go backwards. Right, so let's talk about this a little bit. This point could be seen in a couple different ways. If I had them turn from here back that much, if I had them turn back, you could do it, Jeff. Maybe. Yeah, negative 3 pi over 4. Then they'd have to go back root 2. So you have to go back root 2 if you turn negative 3 pi over 4. These are the same exact points. So if you turn back 3 pi over 4, then you're going to take root 2 step back to get to that same point. Let me let you guys process that.
Is that because
Just you go all the way around.
Yeah, it's just the other way around. If I have the dude turn to face the point, then he's going to walk straight out to the point. He's going to walk positive direction. If I have the dude turn away from the point, and then, okay, walk back, you know, some weird Mother May I kind of thing, then that's the way it's going to look. And I should expect this, because trig functions and all that they have, they repeat their outputs all the time. So there should be more than one way to identify this point. All right, so that's one thing. And I know so far I have not made a good case for it. This makes things easier. Right?
so is that bottom one -1 on the
No,
regular
it's the same as 1, 1.
No, because I told him to turn to
true.
look this way. He's looking this way, but then he goes backwards, so he still ends up at the same point. Good. All right. Maybe. So
if you just switch them around positive, would that? How would you make him go backwards? Forward. If he was at 0, you want him to go down back.
all right. So if I had a point here,
Yeah.
let's say we had a point negative 3, negative 4. I like it. So you can tell him to turn this much, and now we got to figure out what the angle would be, right? This is really good. I like this. So let's look at the point negative 3, negative 4. How do I figure out what that angle is going to be?
Draw a triangle.
What's this angle here going to be? I can figure out what that reference angle is, right?
Minus 180.
Pi over 4 reference angle?
Nope. Got to be careful. If it was pi over 4, the sides should be the same length,
Well, it was 3.
right? At a 45-degree angle, they have the same length sides.
This is 9 plus
So
This is,
what
16 is 5. It's
what trig function would help me out here to figure out what that angle is?
That
Tangent.
is sine.
Let me
Tangent.
draw this a little bit better here. So I've got
Tangent.
4 and I've got 3. Here's theta.
Tangent.
Yeah, it's got to be tangent. Because I don't know the hypotenuse and I don't care about the hypotenuse. Poor little hypotenuse. I will eventually care about it because I've got to know how far this guy's got to turn. So I've got to figure out what this angle is. I can set up this. Tangent theta has to be 4 over 3.
Theta
And actually it's negative 4 over negative 3, but those cancel out anyway.
is 4/3.
So somebody help me out. What do you get for the angle then in radians? How do you solve that equation?
0.927.
Inverse tangent.
Tangent
-1
equals 4/3.
Do it again.
0.9273.
9273, that's good. Is that in the right quadrant?
0.9273.
No, because remember the output of the inverse tangent will be negative pi over 2 to pi over 2. Because that's what the input for the tangent is. Does that sound at all familiar? Remember the inverse trig functions have those very defined ranges, yeah? Oh, sorry. And in fact, you can look at it this way. Do it in, you can change it to degrees since we don't think in radians, and I don't blame you. But one way you got to keep it straight is what's pi divided by 2 roughly? It's 3/2, which is 1.5. It's really 1.57, but 1.5 gets you through most things.
It's like 50,
So where is 0.9273?
it's about 53.
In the first quadrant. It hasn't even made it past it. And I need the thing to be down here. So all I got to do is
Plus pi. Plus pi.
plus pi. Exactly. It's just that much past pi. So I just add pi on this thing. Remember, those inverse trig functions will give you reference angle outputs. We better put them in the right quadrant past that. Inverse trig functions have very restricted ranges. They have an infinite number of angles that they can handle the original trig functions, but there's restricted ranges on the inverse. They only give me reference angle answers. I have to make sure that I end up in the right quadrant. So I know I want my reference angle to be this. I know I want to be past pi by that much, so I just add pi to it. And then round it to whatever. So what's it come out to? Rounded to thousandths place or whatever?
4.0689.
4.0689.
89.
Okay, so now I've got r theta. My theta is 4.069. What's my r going to be? That's the easy part of this, hopefully. 3, 4, 5. Yeah.
Pythagorean theorem? For R we use Pythagorean theorem?
Yeah, definitely. Because this is very much a right triangle. So let's formalize this a little bit. How did we get that r? We did
B squared plus 4 squared.
x squared plus y squared is r squared, right?
Uh-huh.
And how did we get that the theta? Tangent theta has to be y over x.
Yeah.
These are my conversion formulas from rectangular to polar. If I know the rectangular, this is how I convert it into a polar point. Okay. So that was a kick-ass question. Right after you asked it, I'm like, that's an awesome segue into the next thing I want to talk about, which is that. And that's what we got there. So, of course, if I know the conversion from rectangular to polar, I probably want to know the conversion from polar to rectangular. And we already know those. Here's the funky thing about those. The basic idea is I'm at some point, and I know x and I know y. No, let me try to see. I don't know exactly. I know r and I know theta. So I want to go from polar to rectangular. So how do I get x and how do I get y? Given r and theta.
There's a formula.
What do you probably have to use
Like
to
sine?
get this side? Yeah, well, to get this side you need sine.
Uh-huh.
So sine theta equals just the definition of sine theta, really, right? So y equals r sine theta. So I'll bet you anything x equals r cosine theta. And again, sine and cosine are each the percentage of r that's in that direction. The percentage of r that's in the y direction is sine, so forth. I so desperately want at least one person to understand what I mean when I say it. Because it's a really good way to look at it.
Yeah.
I don't use SOHCAHTOA, so.
I can take it.
Really
So that's one set there. And that's all we need there. Right? Given r and theta, how do I get x and y? Bam. We already knew this. Bam. Bam. So let me give you this. Now that I made you write that all out, I've already got it written out on this handout.
Yay! For handout. For formula.
That was really cheap for what it was.
We still
$64.
6 pages.
Well, how many? Did you check?
No.
How many?
Ooh, it's a spider web. I think we still need,
I didn't look up and see how many pages.
we still need,
The details.
we still need
Regular. Yeah, I like paper, so I like paper. The ones that have the spiral at the top.
They're better for like doing homework. Because look what these notebooks right here. We're already this far.
That's crazy.
We have to go measure where they were.
That's what we were doing. So that's fine, that'll be good. I didn't bring that up.
So, just to give you a heads up,
That's it.
if I'm you, I'm going to go look on Google or Bing, depending on which religion you are subscribing to, and look up polar graph paper.
Polar graph
Paper?
Because I am not going to print out a bunch of it for you. So this is really one of the better ones I've found. But it depends on what you like better. Because it shows a decent number of angles. I know it leaves the bottom kind of blank, but oh well, I can deal with that. Because guess what we're going to be doing?
Graphing.
Yes, so we're going to be given equations in polar coordinates, such as r equals cosine theta. Just like we would have x equals 2y or something. And you have to graph it in the appropriate coordinate system. So guess what we're going to be doing? We're going to be making tables of values and plotting them. So we need to figure out exactly how the hell to plot these things. So let me go ahead and do this. Go ahead and do the number 1 and 2 up here. And then we'll do the second part here together. Because I still need to show you there seems to be a missing axis if you think about it. You can turn, but then how do you know how far to go out? Well, you have to identify which circle means what. So, actually, let me give you a little heads up and see if you guys can do this. So you see on there how you have all these little circles. So what I would do is I would go out maybe 1, 2, 3, and then make the fourth one and just kind of color it and make it darker. And that'll be r equals 1. And then 1, 2, 3. And the fourth one after that, that'll be r equals 2. Because then I could very easily plot r equal to 1.5 or 1.25 or 1.1 would be roughly in between 1 and 1.25. You guys kind of with me? Yeah. So I'm setting up the scale on the r. And the r is just distance away. So if I say that 4 circles out is 1, that means each circle itself is 0.25's worth. So that is a scale in a very different way than we're used to, but it shouldn't be that big of a step for us to take. So maybe try that second part out and see if you can plot those points. So do the whole paper. That's what I'm trying to say.